evening.
All right, YouTube is setting up the live stream. Just give me a moment.
Yes, ma'am.
All righty, and we have gone live. So if anyone who is currently in attendance on the Zoom webinar has any difficulty with their audio or with staying in the webinar, we encourage you to hop over to the YouTube page where you can watch live there, and you can enter questions into the chat, and we will make sure that they make it back into the Zoom for Dr. Hill for Mrs. Hill to answer. So if you have questions, that's how you can get them answered. All right, so before we do our introduction, I just want to let everybody know this is going to be through a Zoom webinar. So this is about an hour-long program, and with the webinar features, you can't unmute your microphone or turn on your camera. So you'll be able to ask questions of the speaker through the Q&A function or through the chat. And we will make sure that those get answered during the Q&A session at the end. If you have any questions or encounter any technical difficulty, you can also put that into the Q&A or the chat, and myself or Sherelle will try to help you out. Like I said, you can hop over to the YouTube, watch it live there. And we have some upcoming events as well. We encourage you to visit our events webpage where you can find upcoming presentations in this speaker series. We won't be offering closed captioning today, unfortunately. So if you need that, please watch the recording that will be available on YouTube afterward. All right, so with that, I'm going to hand it over to our public engagement lead, Ms. Sherelle Webb.
All right, thank you, my partner in crime. Hello again, and welcome everyone. My name is Sherelle Webb, and I'm the public engagement lead for the Lunar and Planetary Institute. I'm so happy to have you and Mrs. Dolores Hill in attendance, as well as Grace. So good evening, and thank you all for tuning in for our first presentation in the 2021 to 2022 Cosmic Exploration Speaker Series, presented by the Lunar and Planetary Institute. Our upcoming schedule will feature some incredible science and awesome presenters. We hope you'll join us for future installations. Today, I am thrilled to introduce our guest speaker, Mrs. Dolores Hill. Dolores is a senior research specialist at the University of Arizona's Lunar and Planetary Laboratory. Since 1981, Dolores has studied a wide range of meteorites, specializing in neutron activation analysis, radiochemistry, and electron microbe techniques. She is a member of the public outreach team for NASA OSIRIS-REx mission, and also a OSIRIS-REx ambassador, and is assisting NASA's team as they prepare for the return of samples. Dolores has a lifelong interest in amateur astronomy, and she's even an asteroid named after her. She's helped to lead 2 long-term citizen science projects that are helping to increase our understanding of near-Earth objects through observation made by amateur astronomers. We've honored to join by such a decorated scientist and advocate for public participation. But before she shares her presentation, we do have some poll questions we want to launch beforehand.
Thank you, Sherelle. I forgot about the poll questions. Let me launch this right now.
That's quite all right.
Stop the share. All right. Thanks, guys.
Who's joining us tonight?
All right, so our first question I'm launching now. We're just curious if we have any newcomers here. Have you ever attended LPI's Cosmic Exploration Speaker Series, or CESS, before tonight? So these used to be hosted in person. We've been doing them virtually for a while now. We'd love, oh good, we're seeing some first timers. One of the options is maybe you've never attended live, but you've seen our recording. So that's a reminder that all of these presentations are recorded, and you can watch those recordings anytime, and past recordings on YouTube. All right, so I'm going to stop the poll in 5, 4, 3, 2, and 1. Thank you, guys. We have another quick poll question. We just kind of want to gauge before we start off who we have in our audience. Are you scientists, educators, students, amateur astronomers, community members, and science enthusiasts, or maybe something on here doesn't describe you? And if you identify as other and you want to tell us in the chat, please feel free to do so. Thank you all for participating. All right, so I'm going to stop this poll in 3, 2, 1, and ask for your patience as you do one more, and then I'll hand it over to Dr. Hill. Are you familiar with the OSIRIS-REx mission? Awesome, we have some people who are involved in the mission, people who follow the mission news closely. It is very exciting. People who want to learn more, and then I love it. One of the options is, what's OSIRIS-REx? We're going to learn about that tonight. So fantastic. We're glad we have some people who are just here to learn about this awesome mission. So I'm going to stop this poll in 3, 2, 1. All right, and we'll have one poll question at the end, but you're done for right now. Thank you for your participation. Thank you for coming tonight. And Dolores Hill, please take it away.
Thank you so much. All right, well, good evening. I'm so happy to bring you news about NASA's OSIRIS-REx asteroid sample return mission. First of all, I'm quite happy to report that in 2020, our spacecraft indeed collected a large amount of sample of asteroid Bennu, and it's going to return it to Earth in the year 2023. We expect this to be our country's largest sample return since the Apollo project brought back rocks from the moon 50 years ago. So we're pretty excited about it. And I'm happy to say we collected a lot more than we were expecting. So today I'll report on current plans, the future, a little bit about what is familiar and what is new and different about the asteroid that we selected. And so we thank all of you who joined us on the adventure of OSIRIS-REx. It has been an amazing journey that began in 2011. So with that, let's move forward. And come on. There we go. I want to thank all of those people who over the many years have participated in our community engagement projects. And here's most of them. I may have forgotten a couple, but these were the biggest ones. And we thank you so much for your dedication, your interest, and especially for the Bennu Mappers campaign, where people measured rocks, many rocks, more rocks than we were expecting. And we actually extended that campaign and truly needed your help. So know that every rock you measured was important to us. We thank you. Most people think of the beginning of a mission as the launch. We launched in September 8th of 2016 from Cape Canaveral, Florida, from a perfect day. Some of you may realize that this is hurricane season. There wasn't a cloud in the sky. It was truly amazing. But a mission is more like the birth of a baby. There's a great deal of planning, preparation, building, testing before a spacecraft can actually be launched. And once it is born or launched into space, that's when the science teams begin their initial instrument checkouts and exercise the instruments and their procedures. At this point of the mission, today, we're in middle age, having experienced many successes along the way with more to come. I can guarantee that we are still going to discover things we've never seen before. So it's a very exciting time. So let's go back to the name of our mission. Our mission is actually kind of a complicated acronym, but it fits because it stands for all of the objectives of the mission. O is for origins, because we want to understand the very beginning of the solar system, organic materials that are important to life, spectral interpretation. We want to understand the asteroid that we selected much better. We want to compare that information with information obtained by telescopes and calibrate it, understand where some of our pitfalls or wrong assumptions might lie. And we certainly did that. Resource identification. We were looking for materials that might be important for future space exploration. And I'm happy to say that we indeed discovered water that is one of the most important commodities in solar system travel. People need water to live. Instruments and mining equipment need water for cooling and lubrication. So that was a very exciting discovery already. And security. It turns out the asteroid we selected is not only a near-Earth asteroid, but it's a potentially hazardous asteroid as well. That's an astronomical term, meaning it actually crosses the Earth's orbit in two places. Thankfully, not when the Earth is there, and there's no concern about it in the near future, but this asteroid allowed us to understand how asteroids that are normally stable in the asteroid belt between Mars and Jupiter tend to migrate inward. We learned a great deal about that. In addition, and most importantly, as regolith explorer, that's the last and most important objective of the mission, to return a 60-gram sample of the surface of asteroid Bennu. We want to understand how Bennu formed and its history since that formation 4.5 billion years ago. So regolith is just our scientific term for dirt on an airless body like the moon or an asteroid. But I can tell you it's very precious dirt. We're going to learn a lot from it. So I'd also like to point out that when we selected our asteroid, it was known as 101955 1999 RQ36. That just happened to be the next sequence in the asteroid discovery scheme. At this point, it was qualified to have a name. And so we obtained special permission from the discoverers to have a contest. And we allowed school kids to submit names, and Mike Puzio submitted the best name of all. It had to be an Egyptian mythological creature that had not been used before. And so you can imagine all of the easy ones had been chosen. Apparently, a lot of the school kids selected mean mythological creatures. And so the fact that Mike focused on the beauty of a bird really captured our attention. So Bennu was perfect because it also was associated with the Egyptian god Osiris. So it fit the mission just right. And I have to confess that I was relieved that it was something easy to say and easy to spell. So that worked out great. And incidentally, just last month, Mike himself was honored by having an asteroid named after him. So there's a Mike Puzio asteroid out there too. All right, so let's take a little tour of asteroid Bennu. The names on Bennu, of features on Bennu, are named after mythological birds as well. So that fits the whole theme of the parent Bennu. All of the craters, all of the landscapes, the rock slides are named after mythological birds. This circle in the upper left is our actual sample site. We informally referred to it as the Nightingale site. That's an unofficial designation, and the actual name of the crater is Hokuioi crater. All right, so with that, let me show you where Bennu is located. Most asteroids are located in the asteroid belt between Mars and Jupiter. Some form asteroid families where an asteroid has suffered a collision and the pieces tend to follow in the same orbit. It's pretty amazing that astronomers can figure that out. But asteroid Bennu is what is known as a near-Earth asteroid. And its orbit, as you can see in this diagram, is actually entirely inside a member of either the New Polana family or the Euelia family. Those are both asteroid families. Their compositions are so similar that it's really difficult to distinguish. So we still don't quite know for sure. Bennu, because it crosses the Earth's orbit in two places, it's close enough and large enough to be considered a potentially hazardous asteroid, and that's an astronomical term. Please don't lose sleep over this. It will be thousands of years before Bennu will pose a problem. All right, so when we arrived at asteroid Bennu in 2018, this is what we found. We realized that the shape was exactly what we expected from the radar measurements done at the Arecibo radio telescope in Puerto Rico that unfortunately is no more. But that telescope actually noticed that large boulder on the lower right-hand portion of asteroid Bennu. Bennu is about 500 meters across, or approximately 5 football fields across. When you're standing on the Earth, that sounds big, but in the asteroid world, that's small. So it was a challenge for astronomers to observe. Of heat flow in rocks indicated that there should be very small rocks and a lot of small grains on the surface. When we arrived at Bennu, we realized that was not the case, that there were large boulders and rocks. And so we needed to learn how to navigate in a microgravity environment and come up with a new way of finding a good sample location. We also moved around the smallest solar system object ever orbited. We learned about ground truth comparisons and asteroid materials up close, as well as some amazing surprises. So there's asteroid Bennu with lots of rocks, not quite what we expected. One of the earliest accomplishments was that our spacecraft team was awarded a Guinness Book of World Records award for orbiting the smallest object ever orbited and the closest orbit. Then, pretty quickly after that, we broke our own orbit. So it doesn't sound like such a wonderful thing to brag about, but it turns out that it is quite a challenge to stay in orbit around an object that doesn't trap you into an orbit like the moon or Mars does for some spacecraft. In our case, we needed to come up with a special trajectory in order to stay in orbit and make our observations. So here's how we collected our sample. The sample collector touched the surface for 6 seconds, as shown in this animation. It was actually much slower than that. Once we made contact, we blew nitrogen gas to stir up the material. It got trapped in that cylinder and then stowed away in the sample return capsule. Originally, we were planning to rotate the spacecraft before and after sample collection and look at the change in angular momentum between the empty and full spacecraft to determine how much material that we collected. But you'll see a little bit later why we were not able to use that method. And in the end, that's okay. All right. So I wanted to show you what was going on inside that collector. Lockheed Martin invented this wonderful device called the TAG-SAM, the Touch and Go Sample Acquisition Mechanism. This is a test, an early test in the airplane known as the Vomit Comet, where the astronauts train. So you can guess why it's called the Vomit Comet. It travels high in a curved parabola, and at the top of the parabola, you're weightless for approximately 20 seconds. And that's all we needed was 6 seconds. So once we touched the surface, as you see in the diagram here, high purity nitrogen gas flowed beneath the cylinder, stirred up the rocks, and they got trapped inside our collector. There was a one-way mylar flange that allowed material in but not out. And in all of the tests that we've done, we've collected much more than our 60-gram baseline. In addition, on the bottom of the collector, there are Velcro pads as a contingency feature, so that if for any reason our 3 tanks of nitrogen gas didn't fire, we would have the opportunity to at least collect some particles on those pads. So let's look at another test here. This one is actually a little bit more realistic because we had rocks underneath the collector, so we didn't make a smooth contact. This is actually closer to what we experienced in the real collection event. We touched a rock that we think we may have crushed as we touched it, even though it was gentle. These rocks are about 4 inches across or 10 centimeters. And our tests, that is out of 800 tests done by Lockheed Martin, they showed that we could still have a successful collection. And indeed we did. So on September 24th, 2023, OSIRIS-REx will pass by Earth and eject the sample return capsule. And at just the right moment, it will deploy parachutes that will create a softer landing. It'll still come in at about 100 miles per hour, but the capsule is designed to withstand it. The heat shield, I want to point out, is going to take all of the brunt of the heat generated by the collision with Earth's atmosphere. 80% of that meteorite is actually melted and destroyed as it comes in through our atmosphere. We collected a sample that we are protecting from all of that sort of heat, from our oxygen, from our water. So we are bringing back a pristine sample that will protect it until it gets to Johnson Space Center in LPI's backyard there, where they have built a brand new clean room dedicated just for Asteroid Bennu and Ryugu that the Hayabusa 2 spacecraft returned as well. All right, so here's some of the highlights of the mission. I'll go through a little bit quickly. One of the biggest surprises in our adventure was that there were boulders up to 60 meters across. There were geologically active rock slides, ridges, thermal fractures, and lots of impact craters. It's a wealth of information for people who want to study asteroids and meteorites that come from them. Early on, we discovered water in the rocks. That was a very exciting discovery. We didn't know if Bennu had any water or not, and this showed that it did, and that the minerals in the rocks were actually transformed by that water and trapped. So most of the rocks on asteroid Bennu we expect to be phyllosilicates or clays in magnetite. Also, that Bennu is a close match to some meteorites in the laboratory, but there are some important differences as well. So that is very intriguing. I'm really excited about that. The sun's radiation on Bennu's black surface, I guess I didn't point out that Bennu only reflects 3% of the light of the sunlight that strikes its surface. That's partly why we chose it. We know that it was a carbonaceous asteroid. Because of that, sunlight is absorbed by the surface and gets re-radiated back out into space every time it rotates, every 4.3 hours. That action causes the rotation rate to speed up and its position to get closer to the sun with every day. And you can see there 131 feet per day. Wow. So we were able to measure those things very, very precisely. And the student instrument, RExus, actually discovered a black hole by accident. So that was a fun discovery. And never before seen anywhere in the solar system, particle ejections from the surface of an asteroid. And I'll show you those shortly. So here's a picture of the black hole that was discovered. It's not very exciting, but it's there, and it was confirmed by spacecraft, and was just a wonderful discovery. All right, so let's look at those particles. Wow, look at that. These particles were one of the most exciting discoveries of the entire mission. They actually caused the mission to take a break, pause, and find out what they are made of, how big are they, were they going to pose a danger to the spacecraft? You know, could we continue on with our sample collection? Thankfully, in the end, we determined that they would not pose any problem to the spacecraft. Again, astronomer Carl Hergenrother discovered these totally by accident. For fun, he wanted to identify the star background in the navigation images. And so he was fooling around with the contrast and the brightness of the images. And there was this cluster of stars that he couldn't identify. And he thought, well, those are so bright, they have to be in some star catalog. Couldn't find them. And then he realized, oh my goodness, some of those objects have moved in the short time we took our picture. And that meant that they came from asteroid Bennu. It turns out they all came from one spot. Then we looked at other images and saw other ejection events. Unfortunately, we weren't able to predict where these were occur to catch them in the act, but there were many such events on Bennu. So Bennu is considered an active asteroid now. We actually mounted a campaign to see if there were any meteor showers on Earth that could be connected to asteroid Bennu. And it turns out that if there are, they're very, very low rate. So this is what those particles look like when you follow them in the pictures. And this was very important data because the flight dynamics team and our astronomers were able to study the gravitational field of Bennu by looking at each and every particle. It was amazing to see. And so that information fed back into the spacecraft data and allowed even more precise maneuvers for us. Pretty amazing. We used that information later in the mission as well. All right, so again, continuing on with our tour of Bennu. As with most asteroids we see up close, I think I'm safe to say every asteroid we've seen, there are impact craters. The one highlighted in red is the largest impact crater on Bennu. It's about 130 meters across. If Bennu's 500 meters across, that tells you it's pretty big. It's a significant fraction of Bennu, and it could have disrupted it into many fragments, but did not. Here's another image of a boulder field, and this really got our attention because, oh gosh, that rock that the arrow is pointing to is the size of a dump truck. All those other rocks that look small are actually pretty big. You know, they're the size of a tire or a person's hand. We needed small fragments, 2 centimeters across, or about an inch or so across, for our collector. So this posed a challenge for us to find a suitable place on Asteroid Bennu that would be smooth and not have very many rocks. So here's what we were faced with early on. The red circle is the original 30-meter diameter circle that we needed, or excuse me, 30-meter radius circle that we needed to be smooth with lots of small particles. This would have been a terrible place to touch down. Thankfully, the Lockheed Martin group is so amazing that they told us, well, if we have to, we could actually target a 5-meter circle, get in and out safely. So the science team went to work identifying as many regions as they could that would fit the new criterion. Eventually, we down selected to 4 sample sites, and the Nightingale site is the one that we selected in the end because it had the greatest amount of fine-grained material. It had fresh material. It had organics that we had identified in the spectra. So let's fly over this region, and you can see what a difference the digital terrain model makes. This movie was made using all of the imagery that we captured in the cameras, the theoretical models, and the laser altimetry that was collected to determine how far away we were at any given point. And they were all combined to make a 3-dimensional film animation so that the team, could figure out the correct trajectory to get the spacecraft safely in and safely out without any part of it ever touching a rock. We used a natural feature tracking method and created hazard maps that allowed the spacecraft to build up a library and become somewhat autonomous when we collected our sample, so that it would compare every rock in its library to every rock in its field of view. And if anything was different or out of place, it would wave off the collection. Thankfully, we didn't have to do that. Everything worked perfectly. So I'd like to call your attention to some of the instruments that we had on board. We had everything started with O for OSIRIS-REx, the thermal emission spectrometer built at Arizona State University, the OVIRS, visual and infrared spectrometer, and the OCAMs, the camera suite. Tens of thousands of spectra were acquired by both the thermal emission spectrometer and the visual and infrared spectrometers, processed through a pipeline, compared with each other, calibrated, recalibrated, compared with every orbit, every flyby. It was just amazing. And they were combined in many different ways to extract as much information as possible. Thousands of images were taken by the OCAM suite that is actually 3 different cameras. The Polycam is essentially a telescope. The MapCam allowed us to map the asteroid at large scales, and the SAMCAM documented the sample collection. We use the same filters that astronomical telescopes are used so that our images can be cross-calibrated with telescopic data as well. All right. So the spectra acquired suffer many different challenges. There are different changes in the spectra based on the temperature of the instrument, the temperature of the target below the instrument, different sun angles, the time of day, if there's scattered light on the camera from some other part of the spacecraft, although we were pretty careful to shield it from such things. CCD hot pixels that are problematic for all CCD cameras. It turns out particle sizes and roughness of the surface can change the spectrum a little bit as well. Each instrument had its own different footprint size, and all of those things had to be reconciled so that we could make sense of what we were looking at. So the teams were pretty ingenious. They developed clever methods to isolate information for particular boulders and regions. They identified and measured many different spectral features that I'll show you here. So here's an example of spectra of Bennu. On the upper left, it just shows that we've identified phyllosilicates in the spectrum, the global spectrum of Bennu. And in the lower right-hand portion, we also identified features of magnetite, which is an iron oxide mineral. It's often formed in the presence of water. So the fact that we had both water and magnetite is not a huge surprise, but was interesting information nonetheless. We also identified carbonates in Bennu's surface rocks, and they're probably carbonates. Since I'm a meteorite person, I wanted to show some comparisons with meteorites in the laboratories. So at the very top, you see the spectrum of Bennu compared with spectra of meteorite rocks on the left and ground up meteorites on the right. And the thing I'd like to point out first is that you see there is a real difference. For instance, the Orgueil meteorite at the top, it's Orgueil. Orgueil has one curve when it's a whole rock, but if you grind it up into fine particles, it kind of flattens that curve out. We weren't sure what we were looking at first, and so we used our camera images and the spectra, the laser altimeter, filters, all of the images to try to figure out what we were looking at. Are we looking at fine particles? Are we looking at chunky rocks? Are we looking at rocks with particles on top of them? And how can we figure this out from the spectra? And so the thing I'd like to point out here as well is that the spectrum of Bennu at the top, which is black, is very similar to the other CI and CM meteorites. So the first 3 meteorites on the list, the red one, the yellow one, and the green one, are carbon-rich meteorites in our laboratory that are the closest meteorites we have to asteroid Bennu. But Bennu has some important differences in its spectrum that we have not quite figured out yet. So we will be looking very closely at the returned sample to figure out how and why that is different from the meteorites in our laboratories. As I pointed out, the 2.7 micron water feature in the spectrum of asteroid Bennu was discovered early on, and you can see that it is also present in Ci and Cm meteorites we're showing here. If you take one of these meteorites, I would never do this to waste it, but it has been done for science. If you take a teeny tiny amount and heat it in a test tube, water droplets will come out of the rock. You can be sure that when asteroid Bennu, when pieces are returned to Earth, we will want to analyze the water locked up in those rocks to identify where that water came from originally. Again, since I'm a meteorite person primarily, I wanted to show you some of those analog samples. And so the first thing you'll notice is they're all pretty black. They are dark meteorites. And so we selected an asteroid that was like one of these. We don't know exactly which one until the sample returns home. This was one of the methods that the spectrometer teams used to identify different pieces of Bennu. Even though their footprints were large, the footprint, that is the field of view of their instruments, were fairly large, but they used special techniques to take many spectra and overlap them, compare when an object was in the spectrum and when it was out of the spectrum, and subtract the two things to try to figure out very subtle differences in the compositions of the rocks on asteroid Bennu. It was pretty ingenious. So some of the things that we learned is that space weathering on Bennu is a little bit different than on other solar system objects. That is, as a rock is freshly exposed to space, perhaps in an impact, the rocks normally become bluer. In our case, it's red and they become bluer. Except for a few bright boulders on asteroid Bennu, the composition is very similar over the entire surface. And we identified pyroxene, phyllosilicates or clays, and the hydration products, organics that are probably carbonates as well. And so here are some of those white rocks. We were pretty excited because they have a spectrum that is so different from anything else on Bennu that they stood out very easily. There are at least 6 boulders that are probably from asteroid Vesta, which has a very different, unique composition in the solar system. So at some point in Bennu's history, pieces of asteroid Vesta collided with it and were there waiting for us to discover them. We'll be looking for some of those particles in this returned sample as well. All right, so let's get to our all-important tag maneuver. This maneuver actually took place over a 3-hour time period. So my slide is a little bit slow here, and that's okay because you can imagine what it took to be so patient. Our collection took place October 20th at 2020 at 6 p.m. Eastern Daylight Time. The sampler head touched the surface for approximately 6 seconds. And after that, we conducted a back-away burn to move safely away from the asteroid. So I'll show you a slowed down version of this, we hope here. Okay. Oh, sorry. All right, we'll go back. I'll be patient here, just like we had to be during the real event. The other thing I'd like to point out here are all of those many, many particles. You even see some dashes in the images. That tells us the particles were moving very quickly. We lofted many, many particles, and it's thought that it's possible we filled our entire collector when we first touched down, and that when we fired the gas tank, the nitrogen gas, that we stirred up more material. We don't know for sure, but what it told us is that the surface of Bennu is very, very weak. I want to go back here again. When we touched a rock underneath the surface of our collector, it actually crushed the rock. We had hoped to rotate our spacecraft before and after collection to determine how much mass we collected. And when we moved the collector into position to verify that we collected sample, we discovered, oh dear, there's actually material moving out of the collector. So in the left-hand portion of the collector, you might see a little flange. Let's see, I don't know if you can see my pointer, probably not. It looks like a little dent in a fender or something. That is actually a small bend in the mylar flange that is supposed to keep material inside the collector. We realized that all of those little white particles you see are escaping from the collector. So as time goes by, we're losing mass. We don't want to lose anything. So we immediately stopped all movement, and a decision was made to forego that mass measurement maneuver and go directly to stow as soon as possible without dislodging any more sample. So the silver lining to this dilemma is that we actually think the collector was completely full right after collection. The other interesting thing is that we can see from the tumbling of the particles in many different pictures that they're flaky in nature. And that's intriguing to all of us. We don't have very many meteorites that have flaky textures. So we're looking forward to learning about those. The trajectories of these particles was studied with the same kind of techniques that was used to study the particles being ejected from the surface of Bennu. So that was a bonus as well. So here is the stow maneuver taken by the stow cam, and the engineers commanded the collector to stow into the sample return capsule a few millimeters at a time, and they had to wait 18 minutes for their command to go to Bennu, 18 minutes back to confirm that it was correct, and then send the next one. Can you imagine the amount of patience they had? It was amazing. And they did this right on the heels of the sample collection. We previously were expecting a longer time in between these procedures, but we realized there was no time. So there it is, safely stowed, and there's the capsule with the sample safe inside, ready to return to Earth. And so we conducted our final flyby in April, and we went back repeated some of our previous orbital campaigns because we wanted to understand what the surface looked like before and after. So here we go with the pre and post tag maneuver. And the X shows where we touched down originally, and, well, excuse me, X marks the site where we collected our sample, and the circle shows the boulder that was propelled by our collection. So we definitely stirred up the surface and collected material. We're still trying to understand how deep we collected our sample. And I can tell you that scientists will be thrilled with all of the material that we brought back. So with that, I'll take you back to Earth. This is just a handful of the many, many instruments that are currently preparing for the return of the Bennu sample. We are about to begin sample readiness tests to check out our pipeline of procedures and methods to make sure that we're ready when the real sample returns. So Bennu will undergo tests in laboratories around the world that will answer questions about the early solar system, Bennu's origin and history, now hydrothermal processes on asteroids, space weathering, the nature of organic materials, and perhaps how some of those were delivered to Earth, and much, much more. And so the University of Arizona will be at the forefront of that process, and the best of Bennu is yet to come. We invite you to look forward to the sample return in 2023 at the Utah Test and Training Range. And I thank you so much for your attention, and I look forward to any questions you might have. Thank you.
Well, thank you, Ms. Dolores, for your presentation. So yes, of course, we have tons of questions for you. And I know that our listeners cannot wait for them to get answered, so I'll just jump into them. We have a question in Q&A from our listener, Mark. And his question basically said that the projectile or the debris that's coming from Bennu, is that due to Bennu being active asteroid, or is it due to a collision to another or from another asteroid?
Okay, thank you. Excellent question. At first, we had no idea and thought there could be some combination of volatile materials that were being heated up and causing particles to be ejected off of asteroid Bennu. And we explored the possibility that there were micrometeoroids striking the surface and causing particles to be ejected. We also looked at fractures. You know, there's freeze-thaw cycles even on the Earth that cause rocks to break apart. Bennu, with such a short rotation period where it gets really hot, really cold over 4.3 hours, there's a lot of thermal stresses on the rocks. So there could have been any one of those three processes. We now think that probably the biggest contributor are micrometeoroid impacts, but that all three of those things are in play. So excellent question. Thank you.
Yeah, absolutely. Go ahead, Grace.
Sure. So I have another question. This one was in the chat.
Okay.
This is from Harold. And Harold asks, so Ryugu just was sampled by JAXA, and Ryugu looks a lot like Bennu.
Yes.
Will we be sharing samples with JAXA, which is the Japanese space organization? And was it intended that NASA and JAXA would sample two similar looking asteroids? We'll give Dolores a moment, maybe a little connection issue.
Oh, sorry.
That's okay. You froze for a second.
There we go.
Looks like you're back. There you go.
All right, good. So first of all, I'm so happy to report that both NASA and JAXA have formal agreements to share everything. And I almost put it in my presentation. We actually received a teeny tiny piece of asteroid Ryugu several weeks ago in our laboratory. The professor who received it walked in the door, and I said, "Oh my gosh, I need to take a picture of this moment." And so we have samples of it in our laboratory. So it's been a wonderful collaboration. Did we know they would be, the two asteroids would be the same shape? No. We knew they would both be carbon-bearing asteroids. So let me back up a little. Basically, the Hayabusa 2 team and the OSIRIS-REx team selected our asteroids based on very similar criteria. We had the same requirements. And oddly enough, originally, we were going to go to Ryugu, but our astronomer noticed, oh, there's wonderful radar data over here that shows us the shape of Bennu. That means it has loose material on its surface. Let's go to that one instead. So we set aside Ryugu and went to Bennu instead. And the Japanese team said, well, we have the same criteria. Great, we'll go to Ryugu, you go to Bennu, and we'll compare. And it turns out that they are very similar asteroids in composition. Ryugu seems to have experienced a little more heat or desiccation of its minerals. We won't know for sure till they get back. And Ryugu has a little more water still left on the surface. We don't know if they were ever ever part of the same or parent asteroid up, or but we should be able to help figure that out once we have samples back home. We'll be able to compare those. So I think I hit all those points.
Thank you. We have a follow-up series of questions. I'm going to combine a couple. So we have people who are curious if there are plans for the OSIRIS-REx spacecraft after it sends its samples to Earth, and if there are any plans to use OSIRIS-REx or a different spacecraft to visit the asteroid that's coming near Earth in 2029.
So after OSIRIS-REx passes by Earth and delivers its sample return capsule, assuming all of the cameras and instruments are still working properly, we have the ability to go on to another target, but it's up to NASA whether we have an extended mission or not. And so we are in the process of putting together a proposal for an extended mission to go to another asteroid.
Awesome. Well, I will take up the next question. It's going to come from Douglas. And Douglas asks, at what velocity did the tag maneuver operate at?
Oh, okay. I'm sorry, I don't have that exact number, but it was, originally I was told 10 centimeters per second, but it seemed a lot slower to me.
Okay, fair enough.
it was very, very slow and gentle. It was pretty amazing. And to think the spacecraft was controlled so carefully from such a great distance.
All righty. Well, thank you for that answer. I hope Douglas is satisfied with that one. And I'm actually looking at a question from our YouTube page, our YouTube channel there coming in. Were you going to say something, Grace? Okay, awesome. And so This is from Scott, and Scott said, do we have any good explanation for the thermal inertia on Bennu that leads us to believe it was boulder free?
Basically, it boils down to the assumptions in the theoretical models that astronomers use that needed adjustment. And that's part of the ground truth calibration that we've been talking about between astronomy and the actual real object in hand. So it wasn't, it's not a huge surprise, although we would have preferred an entire surface full of fine grained material, but that's okay. We were able to deal with it in the end. And the rock that held the mylar open in the collector is still there. Because we feel that the rocks on Bennu are very friable and fragile, it's unlikely it will survive. But I can tell you, if it does survive, we will be so excited. We'll be able to do a lot of things with a rock like that. So I hope it does. And we won't know till the first lucky team gets to open that capsule and see what's there.
I know that would be so incredible. And I actually want to go from our chat here now, and then I'm gonna bounce back to YouTube. But here it's, how feasible is it to capture or tow an asteroid?
Oh, I think it would be easier to push it, because to capture it or tow it, you'd have to put something all the way around it, right? And then somehow figure out how to pull it. And so the DART mission is going to actually test how feasible it is to adjust an asteroid's orbit by doing just that, giving it a little bit of a push. That's actually probably the most efficient way of doing it. May not be so dramatic, but it'll work.
Sure. And now going back to Scott, would you agree that the best time to plan an extended mission before the close approach of the Earth for a sample drop off, given that the gravity of Earth can be used to adjust orbit of the spacecraft?
Oh, we were thinking about an extended mission before we launched our spacecraft. So the spacecraft engineers, the flight dynamics people are so amazing. They can adjust our entire trajectory and orbits all along. So they make it look easy. I know it isn't, but they can adjust for many different kinds of targets. Our biggest constraint was that we couldn't get too close to the sun, because our materials weren't necessarily built to get that hot. So we'd like to stay away from the sun if we can. So probably no sun grazing mission.
All right. Well, with that, we're a little bit over the hour, so we're going to wrap up. Thank you, Dolores, for that awesome presentation and for sticking around to do Q&A. Thank you to everyone who attended. I'm going to put up our final polls. So please stick around for just a second to answer these poll questions. Your feedback is very valuable to us. There's 2 questions here. Please answer both. And when you leave the Zoom today, you should be directed to take a survey. And this is a free-form survey. It's anonymous. But again, we would love your feedback on how to improve our programs and how to reach more people. So get these in, and then please visit our education event page. I'll post the link into the chat right now. but we've got an awesome series of talks coming up in our speaker series for 2021 and 2022. We have a lot of thematic talks coming up about the James Webb Space Telescope, which is hopefully launching very soon. So we hope that you all will come back, join us for many more of our events, and just stay excited about all of the amazing missions that are happening. So I'm going to end the poll. Thank you all again for coming. And I will put up our closing slide, but we are done here. Thank you for attending.
Thank you.
Awesome. And I just
And
want to
we will
remind
see you next
anyone
time.
that if there were any questions that was unanswered, feel free to email the education team, and we'll be sure to forward those questions to Ms. Dolores for them to be answered. Thank you again so much, and you have a fantastic evening. We can't wait to see you at our next program. Good night, everyone.